Hello, and welcome to our next section called Velocity and Momentum. Now that you know what speed is and position, you can use those terms to describe motion or to begin to describe motion of different objects. Now we're going to look at some more ideas to help us better describe motion. We're going to look at a term called velocity. You probably have already heard of this term. How is velocity different from speed? They sound a lot alike. We're going to look at that. We're also going to discuss relative motion and reference points. What do these terms mean? We're going to describe that. And we're going to look at a very important aspect of motion called momentum. Let's review a little bit. Remember, distance is simply the length of the path that has been traveled. Displacement, however, involves more than that. First of all, it would be the change in position from the starting position to the final position, not necessarily its entire pathway. And it includes the direction that the travel has taken place. Similarly, we have a difference between speed and velocity that is kind of similar. Speed, it's not as descriptive as velocity. It just talks about the distance that the object travels per unit of time. So for speed, we're simply looking at the distance per time. For velocity, we're looking at all of this and the direction. So kind of like distance is not as complete because it doesn't include the direction, whereas displacement, we're looking at the direction involved as well. Speed and velocity have a similar relationship in that velocity is taking into account direction. It's like saying it's the speed, but it's also the direction I'm going. Is it possible for two objects to have the same speed but different velocities? Yes, it is. How about an escalator? How many of you have ridden on one of these in a department store? Well, these happen to be going the same speed. One, I don't know which is going which direction. Let's say this is going down. Whatever speed that escalator is going down, this escalator is going up the same speed, but they're going different directions. One is going this direction and one is going exactly the opposite direction. Therefore, they have different velocities. Same speed, but different velocities. Another way to think about this, let's take one of these cars, how about this green one, and say that it is traveling at the same speed all the way around the track. Here's its track. It's an oval track. Does it have constant velocity? No. It has constant speed, but it does not have constant velocity because its direction is changing as it is going around this track. It might have constant velocity right here along this portion, but here it does not have constant velocity. Its velocity is changing because its direction is changing. As a matter of fact, the speedometer on that car is telling the driver its speed, not its velocity. Otherwise, we'd call it a velocitometer. Let's say we start this little green car right here. And this little green car, let's say it can instantaneously accelerate to some speed, and it goes that same speed all the way around the track. At this point again, what would its total change in velocity be? It would actually be 0 because it has traveled in different directions. It's all the way back to its original direction, and its total velocity at that point, again, would be 0. An example. Let's do an example and solve this together. Let's say you drive due north for 10 minutes in your car. You travel, in that amount of time, 18 kilometers. What is your average velocity? First of all, I'm going to write down something I do know. I know that speed is distance per time, distance divided by time. And I know that velocity is also equal to the distance over the time, considering the direction also. So we also need to know whatever the direction is that is going in. So I know those formulas. I am given some quantity of time, and I am given also a value for distance. So I know both time and distance. However, minutes and kilometers are not the units I want. Remember, my distance should be in meters and my time should be in seconds because I'm going to want to measure my velocity in meters per second, and I'll tell the direction that I'm going. So what am I first going to do? I need to convert some of these units. So let's do that. Let's take 10 minutes and multiply it by my conversion factor. I know that there are 60 seconds in 1 minute. So I can put 60 seconds on either the top or the bottom and 1 minute on the other side. Which will I put on the bottom? I want to put the 1 minute on the bottom so that my minute units will cancel out. 1 minute is equal to 60 seconds. So there's my conversion unit. I can write that answer down. 10 times 60 equals 600. My minute units cancel out. I'm only left with the units of seconds right here. So it's 600 seconds is the amount of time. Now let's look at converting my distance units so that those will be able to be plugged into my equation. I have 18 kilometers, and I want that in meters. I know that 1,000 meters are in a kilometer for my conversion unit. What do I put on bottom? I put kilometers on the bottom because I want my kilometer units to cancel out, right? I know that 1 kilometer equals 1,000 meters. So when I multiply this out, 18 times 1,000 is 18,000 meters. I'm running into my little picture there. The kilometers cancel out. I'm left with just meters. So now I can turn this into a plug and check problem. It's really easy. I'm going to take my equation now. I can put in distance on the top, distance of 18,000 meters. And I can put time on the bottom. I've just calculated that, 600 seconds. When I divide that, 18,000 divided by 600 is 30 meters per second. And that is my average velocity. I'm looking at the total distance divided by the total time, and I get my average velocity. Next, we're going to talk about something called relative motion. Have you ever sat on a bridge over some water and dangled your feet down looking at the water, and all of a sudden you start to feel like you're moving, even though you're sitting fast on this bridge? That moving water, if you get used to that as your reference point, and you consider that your reference point, you start to feel like you're moving. That's because it's very important. The choice of your reference point affects how you would describe motion. We're going to look at some examples of that. That's not the only example. Think about a person sitting in their seat on a moving train. How would you describe their motion relative to the train? Well, it would be the same. They're moving right along with the train, so they would have no motion compared to the train. But how would you describe their motion compared to the ground or the track that they're moving over? Well, they're moving at whatever the speed the train is moving. So there are many, many examples. Just think of all kinds of examples that you would describe the motion differently depending on the reference point that you're using. Let's take an example here of this house right here and this car. If the house is chosen as the reference point, then the car appears to travel at 10 kilometers west from this frame to this frame. We have our car here, and it is appearing from here to here. It travels, if we look at each of these lines as 10 kilometers distance, it apparently, after 1 hour, this car appears to have moved 10 kilometers to the west from this to here. And The storm appears to have moved 10 kilometers also, or 20 kilometers, excuse me, west. It has been appearing to travel 20 kilometers per hour, and it's made that movement in 1 hour of 20 kilometers to the west. That's if we use the house as our reference point. What if we use something else as a reference point? Let's say we choose the car to be our reference point, okay? Then, in that case, the house appears to have moved 10 kilometers to the east after an hour, and our storm appears to have moved only 10 kilometers to the west. So, we have our house as a reference point versus our car as a reference point. The exact same motion is happening, the same difference in motion over that 1 hour, but the way we describe it is vastly different. You can see if I simply take this frame right here and move it that direction by my 10 kilometer distance, I get the exact same frame as this frame right here. But because I'm using my car as my reference point, I'm just maintaining the position of the car, and then these other things fall in line. So the choice of my reference point will describe how I describe motion, and there really isn't a right or wrong choice of your reference point as long as you maintain the same reference point throughout your problem. Now let's take a look at momentum. And in science, when we talk about momentum, we are talking about a contribution of an object's mass and its velocity. And we'll look at that some more. It's mass times velocity is momentum. So you know this because you know that if you have this big truck and this little car and they are both traveling at, let's say, the same speed, say they're going 55 miles per hour, which one has more momentum? You know that it would take a lot of work for the brakes to stop this object as compared to this object. There is much less momentum in this object than this, even though they're traveling at the same speed. They do not have the same momentum because there is a lot more mass right here. Similarly, if you have someone driving a car and let's say a little insect traveling at the exact same speed, let's say both of them are going the same, we'll have them going the same velocity in the same direction, aiming right at this vase. I have them opposite directions here, but let's say they're going the same direction. They're both right, straight target to the vase at 30 miles per hour. Which one is going to have an impact on that vase? Well, I dare say the fly probably will not. The car, however, will probably break the vase traveling at 30 miles per hour, heading straight for it. That's because there is a lot more momentum here because the mass is greater. Now let's say we have two little flies and they are traveling at different speeds. Let's say this one has a much greater velocity than this one. What do you think the impact will be when they finally run into something? Well, this one will have much greater momentum because it's going a lot faster than this one. So both mass and velocity matter when we're talking about momentum. And let's look at the mathematical equation, because one thing I think is so wonderful about mathematical equations is that they're very simple. I just spent a lot of words explaining things to you when we could simply look at these three lovely little pieces to that equation and understand it all right there. We oftentimes refer to momentum as a lowercase p. Right here, it is the product of an object's velocity and mass. So momentum equals mass times velocity. This is another way to say it. Momentum equals mass times velocity. Mass is measured in kilograms. Velocity is measured in meters per second. Momentum is measured in kilograms times meters per second, or kilogram meters per second. Let's do an example together. Let's say this sprinter is running with a velocity of 10.0 meters per second north at the end of her race, and she weighs 80.0 kilograms. What is her momentum? First, I'm going to write down my equation for momentum. I know that momentum equals mass times velocity. I'm also given some great valuable information. I'm given her velocity in meters per second. Isn't that nice? I don't have to do any converting. And I'm given her mass, 80.0 kilograms. It's in the right units too. So this is a very easy plug and chug problem. I'm simply going to plug in my mass and my velocity in the correct units already and chug away in my calculator and get the right answer. So there they are. I put the values in. 80.0 kilograms times 10.0 meters per second. That gives me 800 kilogram meters per second. And that is her momentum. Advanced ideas. We have so far been describing Galilean or Newtonian relativity when we're talking about relative motion. You've probably all heard of Einstein's theory of relativity. It describes motion of objects traveling near the speed of light. How do the rules change for objects approaching this speed? Specifically, what starts to happen that's different? And what is the speed of light? Find some of those things out, and I look forward to seeing you in class and working out some more problems with you.